Okay, I want to finish up chapter 3, 4, 3. So we'll finish up chapter 3 today. So we will review for the exam on Friday. So we'll review on Wednesday for the exam on Fridays. That's according to the syllabus. So we're kind of on track. We're off by one track. No big deals. But the last thing I want to talk about is actually standard calling convention, calling subroutines or functions from C that are written in assembly, and then also vice versa, calling C functions from assembly. And then also implementation of various C control structures like if statements and for loops or while loops, how to implement those in assembly. And then I'll talk a little bit about the homework problem that I'm going to assign today. We were looking at this last time, implementation of the random number generator in assembly, and sorry, it wasn't working here. I went up to my office and I tried to do essentially the same thing that worked fine. So we'll take the time right now to load this, but you can later. Mainly what I was trying to show you how to do is access storage and RAM. And it's a two-step process. We actually need to set aside space in RAM, and here I'm calling it variable M. Of course, you have several of these, X, Y, count, whatever, with any label, and then the corresponding size, how many bits you want to set aside in RAM. And then the other part is you also need the address of that variable, okay? And you won't know that, okay, when your program's assembled and linked together. It's in that process, in that linking process, where the various variables are assigned locations in memory. So the linker will fill in this address for you, and that's what this does. So this is actually in the code section. So the address would actually be written into flash ROM, okay, so and loaded in when you load the program. So this is the pointer to M, and it says here, load the address of M into this location. That's a 32-bit address. And then I also put the constants into flash ROM. You don't have to do it this way. You can actually move the constant values into a register. But remember, our moves are actually restricted to 16 bits. So you have to shift them up to cover the upper 32 bits. It's a little more convenient when you're dealing with large constants to just go ahead and assign them room in flash ROM and then load them. So the rest of it, I put in here what we're trying to implement. And in here you can actually do everything just using the registers. You don't have to use the storage location and RAM. And here this variable M is it's very much like a global variable in C. Local variables in your functions are actually on the stack. So, and the implementation here, you would never actually have to write the variable out to RAM. We've talked a little bit about the calling convention for subroutines, that you're free to use R0 through R3 and vary those in your subroutine. You don't have to preserve those, but the other registers you need to preserve. Okay, that's your responsibility. And that's a convention. It's one that's used by the C compiler. So when you're writing assembly language routines to interface with C, you have to follow that same convention. They could have chosen a different convention. For example, to make R0 through R6 scratch registers and make then the subroutines responsible for preserving all the other registers. But this is the defined convention. So here, I think I'm using R4 internally to represent the variable m. I'm loading R5, I'm loading the pointer into R5. So initially, this part is just initializing m to 1, moving 1 into register R4, getting the address in R5, and then moving the value into that location. And then here I load the constants into R6 and R7. And I'm using registers here that are, you know, above R3, so I don't have to worry about them being modified by any of the subroutines we call. So this one, output init, you know, it's free to vary R0 through R3, but it has to preserve all the other registers. So if it uses them, it means typically they push those values on the stack and then restore them from the stack before returning. Okay, so that's our output initialization. The rest of it is, you know, part of our, we have these routines that we can use to print stuff to the serial terminal, but the value we pass to be printed has to be in R0. So just move the value of m into R0 before calling the print routine. I had loaded the constant values into R6 and R7. So I just multiply R6 times R4, and then add the other constant. And then this is all that's necessary to write R4 back into the memory location. And you really don't need to do that in this particular program. You can do all of this just using register variables. And then back at the top of the loop, it branches back here. It then moves R4 into R0 so it can print it out. So it's really just these few lines of code that form the body of that. Sorry about the tabbing got all over the place. It looked fine in the editor, but in the web page, it's all over the place. So again, this is up on the website if you want to download it. This is that random number generator that we wrote in C or implemented in C previously. And here's the assembly language implementation. And really, it was just to show you how to access variables in RAM if you need to. Okay. I want to talk about, in a little bit more detail, the calling convention. So, and we'll talk about what's known as the standard calling convention for the ARM processor. So having a standard convention allows you to intermix, you know, functions written in C or C++ with assembly. You know, as long as we all follow the same convention, we can call subroutines written in other languages from whatever language we're writing our code in. But the standard, and then so some terminology, you know, if you took a C programming class, you typically talk about functions or maybe calling functions. Often in Java or in object-oriented programming, instead of functions, they'll use the term methods. Often in assembly language and in Fortran, well, in assembly language, they'll talk about subroutines typically. And Fortran, it's probably never seen Fortran, they would have both subroutines and functions. The distinction was subroutines didn't return values, would be like a void function in C, and functions return values would be the difference. So, you know, whatever you want to call them, calling subroutines, functions, methods, I'll use the term subroutines, but you place the input parameters in R0 through R3. So that gives you 4 possible input parameters with this convention. If you are calling a function that only takes 1 input parameter, like our uint function and int function, you know, it only has to be an R0. What about, you know, it's possible certainly to call functions that use more registers, additional parameters are on the stack. They're pushed in left to right order. So by that I mean, you know, the first 4 parameters, input parameters in your function would be in register int foo a int a int b int c int d and int e, then R0 would have the value A, R1 would have the value B, R2 would have the value C, R3 would have the value D inside your function. So this is how you would access those input parameters. They would be directly available in those registers. E is not available in the register, you have to pop it off the stack. The stack pointer actually points to E. So you pop E, pop off that value in the stack, and then do something with it. You know, an additional parameter, you pop again to get access to that. You know, why didn't they use more registers? They could have. Again, this is the convention. You know, there are 4 registers that are set aside. This is why you can vary those inside your function. You don't want to change them before you read off the input parameter, but after you do that, you're free to. Of course, the way C works, changing A, B, C, or D inside your function doesn't change the corresponding variable back in your main root. This is a copy of whatever you pass here. You know, the actual variable is copied into register 0. So we change it, but we're not changing the original variable back in our calling routine. How do these functions return a value? The return value is in R0. So before we come back, we need to make sure R0 holds whatever we want it to hold, you know, the sum of these 5 input values or whatever. And your subroutine may change R0, R3. Subroutine must preserve other registers. Typically, by pushing them on the stack. Of course, when you push something to the stack, you always want to pop it back off too. So I've got a simple example here. So bring up Code Composer. I've got a simple example both of calling an assembly routine from C. That's the first one we'll look at. And then also calling a C routine from assembly. So I'll give you a few minutes to bring up Code Composer Studio. Now, you could copy a project here, that would be fine, maybe a little easier, but I'm just going to create it from scratch. So you want to be able to do that. So new Code Composer Studio project. And then here we're just going to create an empty project because it's got the C main for you as well as the assembly file. And then we'll call this one call assemb from C. And okay, all good there. So now up on the website under today's, so 354 lectures, lecture 12, calling the C from assembly. Here's the C program. We're going to write a function that adds the two parameters and returns the result. Our C program prints out hello world, calls our function, and then prints the result of the function. Okay, so this is pretty standard C. The only thing that, this would almost be like a program you would write for a computer, except we have to do the output initialization so that it writes out to our serial port. And then the other thing we're going to do is actually write add to in assembly. So right click on this and save the link as, and then save it into your workspace into this particular call assembly from C. Okay, here this is the main.c program. If you take a look at the add2.s, really couldn't be much simpler. Now, one of the things I haven't been doing because we haven't had to do this, and it's not, you don't have to do it here, okay. But I push the link register on the stack. The reason you'll typically want to do that in any functions you write is if your function calls another function, it overwrites the link register. So this one doesn't, so it's not necessary to do that, but it's good practice. So in here, if I called like printint or print new line or any other function, remember the link register holds our return address. Now I'm in a function that I need to return back to main, so I have to preserve that link register. So typically what you do is just push it on the stack. That's the easy way. Then I can call any functions. Before I return, I want to pop it back off the stack. Remember, your pushes and pops have to be balanced. So if I push other stuff on the stack, I have to pop it all back off, and then pop the link register back off, restore the value, and then BX returns me back to the next instruction after main. But my function code here is really simple. The two input parameters A and B are in registers R0 and R1. Just add them together and store the result in R0. That's where the return result goes, right? So it's almost as simple in assembly as it is in C for this particular function. And I could make it a little simpler because I don't call any subroutines. I don't really need to push and pop the link register here. So it's really just two instructions, the add and then the return from subroutine, which is the BXLR. So save this into the same project. Now we also need to remember add our UART stuff because we use that. So again, that was in your workspace, under your workspace in a special folder. So grab all three of those, the simple IO, UART.c and the UART.h. And then again, we want to link to them instead of copying them. And then I'm going to actually build the release version of this instead of with all the debug stuff. So switch it over to the release. Hopefully it should compile. I'm going to bring up the serial terminal PuTTY just so you can use the built-in terminal. So it's finished building. And what this got some errors. Oh yeah, I don't know where this crept in. If you're getting this uint32 in uart.h, it's an error in uart.h. It uses a uint32_t data type, but that's not defined. So it's defined in a header file. So the standard integer header file, standard int.h. So again, just adding it here, and this is editing the original file, so it should be a permanent change. But if you're getting that error message, do that. Okay, and then, so let's try building again here. Got a warning. Add to implicitly declared in main. We can fix that. What that means is it's just a warning. I'm calling a function here, and the compiler doesn't know the prototype. There's no header file in which the prototype for the function is defined. I'm just going to define it right here. It returns an integer type, and then it takes as parameters 2 ints. So this is just to keep the compiler happy. It should run fine even without this. Okay. So now if you notice here, you can make this a little fancier by incrementing A or something every time through the loop. I call add 2 in this infinite loop with A equal to 10 and B equal to 23. Feel free to change these. I'll change it to 45, change it to whatever. What it should print is it's gonna print hello world, and then it'll print the sum of the whatever 2 numbers. Okay, so, and then since I'm not changing them inside the loop, you'll see the same sum. But since I changed it, I'll go ahead and recompile. Hopefully this will be for the last time. Is everyone okay? Any errors?
What did you include in that .h?
In the .h file, so in the uart.h, stdint.h, you could put it in your main, but it has to be before you include the uart.h. It's probably better to put it right here. So now transfer it over to our board. It may already be running for some of you. This computer is really slow. It's probably because I'm running Zoom and everything else on it. But I turn on the recording. And then, so it's finally started running for me. It's printing hello world at 55, 45 plus 10. Okay, just in an infinite loop. So the idea here, behind this portion of the course actually is to give you a better understanding, hopefully, of what happens when you call a function in C. How the input parameters are passed to the function. I'm not gonna, one good way to learn assembly is in your C programs, you can tell the compiler here to produce the corresponding assembly language code for you to look at. So I'll show you how to do that. I don't want to take the time to do that today, but it's a good way to actually, you can see the C source code and you can see the corresponding assembly language. So it's a good way to figure out, how to do something in assembly, that's written in C source code. So any questions about this? Okay, I'm not going to take the time. I will encourage you to do this. But the other thing, what we've had is a main program written in assembly. And again, although we never actually return from our main programs, we just have this infinite loop. So again, it's not really necessary to push the link register. But main is a function like any other function. You're supposed to ultimately return from it. On PCs, you do, and then control returns back to the operating system, right? But here on our microcontroller, we typically end with a while one loop, and we never actually get to a return from main. But again, it's good practice to actually save the link register and then pop it off right before we return. Well, here's essentially the same code, but now our main program is written in assembly. So here I move 33 and 44 into the first two registers, and then call my subroutine with BL. That's my call subroutine. Branch to this subroutine. So I've got the two values in the registers, and then it returns, the result is already in R0, which is where print int expects its argument to be, so I can just call print int and print new line. Again, then we'll wipe out R0. I didn't preserve it. I could have, if I wanted to save the sum, I could have moved it into a higher register before calling print int. But in my while loop, it's always just computing the sum of those two constants. Storing it in R0, and then I'm printing it out, and then branching back to while. And if you look at, so what does the corresponding C routine look like? In C, returns the sum of the two input parameters. But now we really know what's going on underneath the hood, hopefully. Remember, everything in C is translated into machine code or assembly. What's really going on here is, we could probably look at, no, I'm not going to take the time to do that, but if you look at the corresponding assembly language, this routine is adding R0 and R1 into R0 and then returning it. Probably looks very much like our two-line assembly program that we had previously. This is the equivalent in C. So, any questions? Okay, the last thing I wanted to look at is just control flow. Things like your decision structures, your looping structures in C, and how you would implement those in assembly language. And I encourage a very structured form of assembly language. So, kind of write it using pseudocode or block diagram or whatever, at some higher level. And then, maybe in C, but let's say you wanted to implement an if structure. And in assembly language. So what would the equivalent, you use things like this all the time in C, right? It's one of the basic structures. So I typically label the start of every one of these decision structures. We'll actually never use this label, but it doesn't hurt to label the start of the if. And then I'm going to assume that we've loaded the value of n. It could be a variable in RAM, but it's more likely if n is a local variable, it's a value that's on the stack, but I'm going to assume that it's actually stored in R0. So all we need to do is compare R0 to 100. What the compare does, it essentially subtracts the two values and then sets all the corresponding flags. The 0 flag. So if they're equal, it'll set the 0 flag. If they're not equal, they'll set it won't set the 0 flag. Now, and then if you look at the branch instruction, it's got all these different versions of branch. Okay. Makes it really nice. There's a branch of greater than, BGT, branch of greater than or equal, branch of less than, branch of equal, BEQ, branch of not equal. So here we want to branch is greater than or equal because we're actually testing for, and you could lay this out differently. So I'm going to branch if n is, if it's not less than 100, then it's going to be greater than or equal to 100. And that's my else clause. Right? So right under the comparison, I'm going to branch if greater than or equal to another clause later on. And then here, I would just add R0 and 1. Right? Just have to increment the value. This is the main body of my if, okay, the body of the if. Now you have to be a little careful here. I just can't fall through to the else. I have to branch. That's because I want to jump over my else. So we'll have an end-if statement. Then here's where my else body is. Here I do nothing more than move into R0 minus 100. And then both of them then would fall into my end-if, which is whatever is below my if. Okay. So this branch is simply just skipping over that one instruction that forms the body of my else if. Now, if you actually look at the generated assembly when you compile a C, it's got some standard syntax for creating these labels, but it's not human readable. It's just some arbitrary off. I think they just CC something 01, 02, 03, 04, 05. It just generates them, but they have no meaning. But when programming an assembly, I like the somewhat meaningful labels written in C programs. We may have several if structures, so I typically just number them like this to keep track of them. Any questions about what's going on here? So this is a C structure, and this is the corresponding assembly. About the only other thing we need to know how to do that comes up a lot is looping, right? So ifs and loops that's 99% of your programming in any language. By the way, I guess it is important to know because in the homework assigned today, like how do you pass an array? You know, if you write a function that maybe adds up all the elements in an array, and then you pass into your function the array, what actually gets passed? Do they push all 100 elements of the array onto the registers and on the stack? You know? What actually gets passed is the address of the first element of the array. So it's just one parameter. But in that case, when you call a subroutine and you pass it an array, it actually pushes that 32-bit address. It doesn't push the first value of the array. So you actually have to use LDR on R0 then to get the first element of the array. Typically in C, the second parameter then is the length of the array. Sometimes you might use a null terminated array, but if you do that, you can't have zeros in the array. So typically, you know, if you're doing work with arrays and C, you know, so what it would look like is int, you know, add array, int star array, int length, right? But here, when you call this, you know, back in your main program, you would int x10, and then you have your code, and you'd have R is add array. The name of the array is actually equivalent to a pointer to the first element of the array. So it's just shorthand. And then, actually, in this case, it's got 10 elements, 0 through 9. This is exactly the same as the address of element 0. So you could also do that. That's an ampersand. I can't draw one. But it's the address of the first element of the array. You could also use that in place of x. The name of the array is shorthand notation for the address of the first element in the array. You also have to know, as the programmer, whether they're ints or bytes or shorts, right? Because when you use LDR with the address, you have to actually load, you know, a 32-bit value or a byte or a short. Okay, so let's say sum equals 0 or n equals 0, n less than 100, n plus plus, sum is equal to sum plus n. Okay, so this is just going to add up the values 0 to 99 and then tell us what the sum is. So what's the corresponding assembly language? So I'm going to use R0 to hold the sum. And then I'm going to use R1 to hold n. You could use any registers. And then, actually I didn't lose, well, I'll just put my label in here. 401, that's a label. And then, so it doesn't have to be on the same line. I'm going to add the two registers, store the result in R0, which is where my sum is. And then I'm going to increment n by 1. So this is sum equals sum plus n. This is n plus plus. Then I want to compare R1 to 100. And if it's less than 100, I'm going to go back to my for loop and do this over again. Go back to this label. So if R1 is less than 100, after this DLT, this would be the next instruction it would add again. When it gets equal to 100, it does the next instruction after the branch state, whatever that is. So this would kind of be the equivalent of this for loop. Now, obviously, it's a lot more convenient to program in C than it is in assembly. It's just harder to keep track of everything in assembly, but you can. Sometimes you're forced to program in assembly. Like I said, if you're writing an operating system, there's typically the task switching portion of the operating system that has to be written in assembly because it's responsible for saving all the registers every time there's a task switch. And occasionally processors have certain features or certain special instructions that aren't available in C. So you have to write, maybe a function in assembly that you can call from C that accesses those instructions. Typically, you put those in a library so that somebody could get access to those instructions without having to use assembly. So any questions about that? Yes.
So like the branch list, then you don't have to call that immediately after you call it anytime.
You have to be careful that the flags aren't changed by some other instruction. Okay, so yeah, so on a lot of microcontrollers, the adds and subtracts actually will automatically vary the flags. And on the ARM, they only vary the flags if you put the S after it. So yeah, this could be later as long as you haven't modified the flags in between. So, and look at the documentation for each instruction to see whether or not it modifies the flags. Typically it doesn't. Compare, you don't have to add the S because that's the only purpose of compare. Compare does not modify, this could be two registers. It just does the subtraction but doesn't store the results. And that's typically how you test for equality, is just subtract one value from another. Anything else? Okay, I'm going to give you one homework problem today. And it's not hard, but I'll give you the main program in C that adds up, that calls your function. Your function has to add up the elements in an array and return the result. So, and your function will receive the address of the array in the first argument in R0, the length of the array in R1, and then it needs to return the sum in R0. And I'll provide the main routine that calls your routine and actually prints out the result. All right, that's it for today. So we're done with the first 3 chapters. We'll review on Wednesday and then for our exam on Friday. Get you need the book and everything, right? Yeah, put it in the right, yeah, a less than sign. Oh, STVINT. And then that needs to be, the brackets around it. Yeah, less than and greater than. Now, yeah, those. Where's the less than? No, it needs to be that character. Yeah,
Okay. The one down.
because that's one of the standard headers, yeah.
I like that.
And then that's the mic.
And then at one point, so that-
Oh, there's.